Hi everybody, today we are going to continue talking about exponential functions, and we're going to talk a lot about calculating interest, including eventually compound interest using exponentials. So we've talked a little bit about compound interest previously, and the first question here talks about comparing two different accounts. We have one account here that has an initial investment of $50,000 and it's in a compounded annually at 5% account versus a second investment that is 30,000 and again compounded annually with an interest rate of 8.5%. So essentially, to start here, we have two different equations. The first one, we have 50,000 being compounded at 5% annually, so we don't have to worry about calculating any kind of different yearly compounds. We'll talk about that a little bit later. And then we have our second account, right? And that's going to be the $30,000 account that gets a slightly higher interest rate at 1.085 and then to the t power, right? So if we compare these two over 20 years, so I'm going to type these into the calculator, and we're going to have the $50,000 account, 0.05 to the t, or the x in this case, oops, close that, to the x, and then we also have $30,000 account, and we have the $30,000 account at 1.085. Now we're going to set our window this time because we want to look for the first 20 years. So 0 to 20. Kind of can depend on how you want the scale. We'll go there though. And then hopefully we're making a decent chunk of change here. So let's say to maybe 150,000 just to play around and see if we need to adjust it. We can, and maybe go up by 10,000 at a time. And if we check out the graph, what we're going to see is that for the first 15-ish years, this first account is going to be our better option. But if we are able to keep this in the account more than 15, 16 years, it's really going to do us a benefit to have this in the second account, because even though it's less money, the interest rate is higher. And if we want to double check exactly what the amount of time is that we want to check this out for, we can look at calculate and intersect, so second trace to get the calculate, and then we can kind of calculate where this intersection is actually occurring. And what we're going to see here is that, yeah, right around, if you're going to stay 16 years or more, you definitely want to go into that second account. So we can kind of start comparing and contrasting the two. So again, account 1 for years 1 through 15, and then anywhere beyond that, 16 to 20, that's when account 2 is going to be the better one. So that's a lot of what we're looking at here, is comparing those interest rates. And over a long period of time, again, the interest rate really begins to play a difference, is what we're seeing there. Now, we also have other compounding types besides annually. So for instance, compounding quarterly, and that means every 3 months or for a total of 4 times a year. So when we talk about a nominal interest rate or an annual interest rate, but if it's compounded quarterly, really that's going to change our rate. So for instance, if we had our 5% account compounded quarterly, really we're taking that 5%, and again, quarterly means 4 times a year. So really that interest rate turns into 1.25%. Okay, so if Margaret is investing 5% compounded quarterly, what we're going to do, we're going to see at the top of the next page on page 53, is that that's going to start affecting our account, because after 3 months, that's going to be compounding this account 1.25%, right? That one time that we have that 0.25. Oops, I forgot my 1.25, right, to the first. And then after 6 months, that's compounding that same thing we just had, but now to times it's compounded. So it's been 6 months, and then keeping with the pattern, we see it, oops, 1, 2, 5, 3 months, and after 1 full year, that's 4 times that it's been compounded, right? Because it's every 3 months. So what that means is after 4 years, really it's been compounded 16 times, because it's the 4 times a year times 4 years. So we would see 50,000, 1.0125 to the 16th. So to kind of just check on it after T years, we're going to have that $50,000, the 1.0125 to the 4T, because we have to account for that every 3 months. So what this is kind of showing us, if we divide it up even further, is that A of T is going to be that principal value, right? And then 1 plus our nominal rate per year divided by the number of times we're compounding to the NT, right? This is kind of a formula you've potentially seen previously before this class. Now, similar to what we've talked about in previous lessons, we also are going to be able to figure out things like doubling time, tripling time, whether we're talking about a nominal interest rate or a regular or a compounded n number of times interest rate. So to double Margaret's $50,000 initial investment, and again, we're going with this 1.0125 to the 4T, right? Again, we've talked about a couple ways. You can definitely graph this and calculate the intersection. But if we're going to start solving, and this is going to become important to us in Activity 5, to solve for these exponentials, I'm going to start by dividing by the 50,000 so that we get the exponential kind of isolated here. Okay? And we're going to use logarithms, which again, we're going to keep talking more and more about in their properties. If we can take the common log of both sides, the property of logs allows us to bring that exponent out front. So we have log 2 equals 4t times log of 1.0125. And then if we want t to be isolated completely, we're going to have to divide by 4 times the log of 1.0125. Now be careful to put this in parentheses to make sure we get all of this divided, and especially if you have an older calculator like I tend to use, you will get everything underneath properly where it's supposed to go order of operations wise. So that we check this out, we have log of 2. So log button 2 divided by parentheses 4 times the log 1.0125. We end up with right around 14 years, right? 13.9, aka 14 years if we're rounding up, before Margaret gets her money. Okay. Now, if we can change this interest rate, right, part 6 here, if we can, how much less time is going to be required if we to double the money at a 5% compounded quarterly than the 5% compounded annually? Well, if you remember from the last lesson, the annual one was about 15 years. Okay, so the quarterly one saved her about 1 year, but you could get that interest rate there. So it's about 1 year less. Now, if we keep calculating these values, okay, so if we see here, if we start calculating the yearly rate, we actually did this before. So if we check this out, so 50,000, and we're looking at the 0.05. If it's annual, it's n times, right? It's just 1. So if we're going to calculate for 20 years, we calculate this in, it's going to be right around 132,664.88, right? Now, if we go quarterly, we're changing our n value here to a 4. So be careful when you type this in. You want to make sure you can type this all in as one step, but you want to be careful. 1 plus 0.05 divided by 4. And then make sure, again, if you have an older calculator like myself, the 4 times 20, if you're not going to just make that 80 from the get-go, you use parentheses there. We see we have $135,074.25. And if we change this to compounding monthly, what's going to change is, again, that n value. So we plug this in, we're going to have divided by 12, because monthly means 12 times a year. The 12 times 20. So here's the answer to part C. And then we can even go as far as to say daily on this. So we're going to change this to divided by 365 to the 365, and then again 20 years. And what we're going to notice here is that we have a lot less of an increase between each of these each time than we did the previous one, right? We're getting really, really close to kind of topping out here at just almost 136,000, right? So what we're noticing overall here, just to kind of summarize some stuff, is that our rate decreases with more compoundings, right? Because we're going to divide that R divided by N. So the rate is decreasing as our number of compoundings increases, right? And it goes back to that, right? Because it's getting smaller. But what we're noticing is our overall money is increasing with more compounding, right? So compounding kind of is to our advantage if we can get it, because it's going to give us more money in the long run in our accounts, okay? So what happens if we can just start with the dollar here, have an interest rate of 100%, and increase our compoundings a lot here, right? Well, let's think about our account as it stands, right? So far we've talked a lot about this with our principal, 1 plus r over n to the nt power, right? Well, our initial compoundings, they said, is $1, right? And our interest rate's 100%, aka 1 as well. And for the sake of typing this into our calculator, what's changing here is our compounding. So that's going to be our variable x. And our time that this is in the account, it's going to be within 1 year. So really our t value is also what? So as we type this into the calculator, what we're going to see is this right here, right? So 1x, right? Because I forgot about the n's being x each time. Okay. So if you haven't seen this before, something that's kind of nifty on your calculator is if we type this in here, we have 1, we'll leave the 1 off, 1 plus 1 divided by x to the x power. And what we can do is we can set up our table so that we can plug in the values we want on it. So if we look here at second window, we can set up our table so that we have an independent variable versus a dependent variable, which is going to allow us, when we now second graph go back into our table, we can start filling in these values that are on the table from our book. So 100, 1,000, 10,000, 100,000, and finally 1 million. And what we're noticing is as time goes on, and even if we kept going bigger and bigger and bigger in this chart, what we're seeing here is that our account balance is kind of topping out at about $2.07-ish cents, right, is what we're seeing with this table. So this number, and this is why we're going to combine this lesson and lesson 4.3, actually has a very special place. So we're going to move on to 4.3 real quick, just to show you a special value. Notice that this ended here, with the value of this, right? What this is known as is the letter E. So we all know about pi. He gets a special spot on our calculator. We have pi, right? 3.14. He's kind of the most famous irrational number. Our second most famous irrational number is the letter E. So second division sign here, that is letter E. And he's also stored in our calculator. That's the 2.718 that you hopefully noticed again from our table in the previous lesson. So that is where our PAL, the PERT formula, comes from. It's the compounding continuously formula because it's approaching that E value that our other formula went towards, okay? So again, this was from the last lesson, but we noticed we had the compoundings getting closer and closer and closer. If we used PERT then to calculate, what we would see is that it would be really close to the almost daily number as well. Okay, so that's our compounding continuous formula. All right, now this next piece here asks us to compare which accounts, and to save us some time, I'm going to kind of skip over it, but it's really similar to what we just did in 4.2 way back at the beginning of your notes, that you wanted to be able to compare at which point in time are we going to have the best account for us. So you'll do some of that with the practice as well. So I'm going to kind of skip over it to save some time. And finally end here with these last couple of questions. So talking about depreciation, we've talked a lot about appreciation so far in growing accounts, but we also want to take into consideration depreciation. Now, normally, when we talk about, the 1 plus our R value, it would be changing that to a minus. But with PERT, what's going to happen is it's going to change your R value to be negative, is what depreciation is going to use when we talk about continuous depreciation. So if we were to write a function to represent this, they want us, I'm going to call this B of X just because we're talking about a boat here. And it says that our boat initially is going to cost $10,000, but it's continuously depreciating. So that's where the E to the RT is going to come in. Well, negative 0.17 is going to show that depreciation rate with our continuous compounding, right? It's not 1 minus because of the continuous compounding. And then again, to the T, or in this case, X power, will help us represent that. And now that we have this lovely formula, we can just plug in our X value to represent our boat depreciating. And on the calculator, just to show you guys here, 10,000. So the E, a couple places you could take it. Again, the second division sign, but second ln is going to bring us straight to the exponent, negative 0.17 times 15. And we get about $780.82. They always say boats are the worst investment you can kind of have, but see why with such a big depreciation rate on that. Okay. And one last thing, we like to talk about that half-life, right, depreciating. We used to talk about doubling, and now in the case of this boat, let's talk about solving this so that the boat is worth half of its original value. So that would be $5,000. Very similar, and again, we're going to work a lot more with logarithms coming up here. But to start, we're going to divide by that 10,000, so we get 1/2, or 0.5. And again, we're going to work more with this, but to undo this base of E, we're not going to use our common log, we're going to use the natural log outlet. And what's going to happen here is these are going to kind of cancel out, if you will, these two here, and we're just left with that exponent. So ln of 0.5 equals negative 0.17x, and then we can divide by the negative 0.17x, negative 0.17, to get our x value of about 4.077 years. And ln, just to clarify that one too, here's ln 1/2 divided by negative 0.17. Okay. You also are free to, of course, do an intersection here. You can always graph this function that we had. Again, we had the 10,000, then the e to the negative 0.17x, and play around to look for where is that intersection going to occur between these two values. You're going to have to play around a little bit with your window, because you're probably only going to need not the answer about 0 to 10 years, and we definitely don't need to go quite so high on our scale. Probably, we're maxing out at 10,000 as it is, and maybe go up by 1,000. And you can graph to check out where this intersection between those are going to occur, and it should be again at that 4 years marker. Okay, so see right around here. All right, thanks everybody. Just to kind of summarize some things in case you didn't get either of these jotted down, I would definitely make sure you have both of these two formulas in your notes somewhere handy. A reminder, if we're talking about annual compounding interest, it's really similar to this formula, but you wouldn't for annual need to account for your n. So that's why our annual interest formula just looks like 1 plus r to the t. Okay. Thanks, everybody.